Hello friends, today we are diving into one of the most influential papers in empirical finance, Rozeff and Kinney's 1976 study that first rigorously documented the January effect. In this notebook walkthrough, we'll reproduce the core statistical methodology from scratch, generate synthetic data that captures the stylized facts they found, and implement the exact tests they used, Kruskal-Wallis, Siegel-Tukey, and parametric ANOVA. We'll also visualize the monthly return distributions and estimate characteristic exponents to understand the tail behavior. By building everything from the ground up, you'll see exactly how the statistics work and why the January effect is so robust. We use our standard scientific Python stack, NumPy, SciPy, Pandas, and Matplotlib, with a fixed random seed for reproducibility. The Matplotlib settings give us clean publication quality figures matching the paper's analytical style. The statistical framework is elegant in its simplicity. The paper models monthly returns as a month-specific mean plus IID noise. The null hypothesis is straightforward. All 12 months have the same expected return. If we reject this, it means at least 1 month's distribution differs from the rest. The key equation is RTM equals μm plus V R epsilon t, where the subscript m indexes the calendar month. Rejection of H0 would mean expected returns depend on the time of year, a direct challenge to the constant drift random walk model. We generate synthetic monthly returns calibrated to match the paper's key findings. January gets a mean return of 3.5%, nearly 3 times higher than any other month. February and June are set near zero or slightly negative, while December and November are moderately positive. The volatility is set at 4.5% monthly, which is realistic for a broad market index. This gives us 840 observations, 70 years times 12 months, matching the paper's sample size. The sample means confirm our calibration. January stands out clearly from the pack. The visualization makes the January effect immediately obvious. On the left, the box plots show January's distribution, highlighted in red, sitting well above all other months. The median, quartiles, and even the whiskers are shifted upward. On the right, the bar chart of mean returns makes it even starker. January towers over the rest at roughly 3.5%, while the overall mean is closer to 0.7%. This is exactly the pattern Rozeff and Kinney documented. The visual gap between January and the next closest months, December and November, is substantial even in our synthetic data. Now, let's implement the core statistical test. The Kruskal-Wallis test is a non-parametric alternative to one-way ANOVA. It tests whether multiple samples come from populations with the same median. The key equation uses rank sums rather than raw values, which makes it robust to non-normal distributions. This was critical for the paper because stock returns have fat tails. They follow something closer to a stable Paretian distribution, not a Gaussian. The test statistic H is approximately chi-squared with k-1 degrees of freedom. In our case, 11 degrees of freedom for 12 months. The Kruskal-Wallis test gives us a definitive answer. The H statistic is large and highly significant. We reject the null hypothesis that all months have the same location. This matches the paper's finding perfectly. The pairwise Mann-Whitney tests drill deeper. They show January is significantly higher than nearly every other month at conventional significance levels. The triple asterisk indicates significance below the 1% level. And you can see that January dominates across the board. Even the stronger months like December and November show significant differences from January in many cases. The parametric ANOVA confirms the non-parametric results. The F statistic is highly significant, rejecting equal means across months. Bartlett's test checks whether the ANOVA assumption of equal variances holds, and it does in most cases, which validates the parametric approach. The key contrast, January versus all other months, shows a substantial premium. On an annualized basis, the January premium is enormous, roughly 20 to 30% above the rest of the year. That's not a subtle effect. It's economically meaningful, not just statistically significant. This heat map reviews the January effect across the entire 70-year sample. Each row is a year, each column is a month, and the color represents the return magnitude. Green means positive, red means negative. Look at the January column. It's almost entirely green. Year after year, January delivers positive returns. Compare that to February or June, which show a much more random mix of red and green. This kind of persistence is exactly what makes the effect so compelling. It's not driven by a few outlier years. It's a structural feature of the data. The final piece of the puzzle is the characteristic exponent, which tells us about the tail behavior of the return distribution. The key question is, does the shape of the distribution change by month or just the location? An alpha of 2 means normal. Anything below 2 means fatter tails than Gaussian. The paper found alpha values between 1.6 and 2.0 across months, with no systematic pattern. This is important. It means the January effect is a pure location shift. The tails don't change. The distribution keeps its shape but slides to the right in January. We implement the Fama-Roll order statistic method for estimating the characteristic exponent. The key idea is to compare the ratio of the interquartile range to the interdecile range. For a normal distribution, this ratio is about 0.504, and it decreases as alpha drops below 2. Our estimates show alpha values clustering near 2.0 for our synthetic data, which is expected since we used Gaussian noise. The paper found values around 1.6 to 2.0, suggesting fatter tails than normal. Crucially, the alpha values are fairly stable across months, confirming that the seasonal effect is the location shift, not the shape change. This final visualization drives the point home. The left panel shows cumulative returns from investing only in January versus only in February through December. January alone, just 1 month per year, accounts for a disproportionate share of total cumulative returns. The right panel shows the monthly seasonal pattern with standard error bars. January's bar, in red, is both the tallest and statistically separate from the rest. The error bars don't overlap with most other months. This is the January effect in its purest form, a persistent, statistically significant, and economically meaningful calendar anomaly. To summarize, we've walked through the complete statistical toolkit that Rozeff and Kinney used to document the January effect. The Kruskal-Wallis and ANOVA tests both decisively reject equal monthly means. The effect is a pure location shift. The distributions keep their shape but slide rightward in January. And the magnitude is substantial. January alone accounts for a hugely disproportionate share of annual returns. This paper launched an entire research program on calendar anomalies that continues to this day. The tax loss selling hypothesis remains the most popular explanation, but the debate is far from settled. Thank you for watching, and I will see you in the next paper breakdown.